Hi there. Thanks for joining us on a Q&A edition of Space Nuts. My name is Andrew Dunkley. Thanks for your company. On today's episode, questions from the audience. Rusty is asking about the similarities between the sun and the moon, and there are several, and most are coincidental, as it turns out. Trevor wants to talk about speeding through space. Slap a couple of P-plates on and you're on your way. Austin has asked us about Hoag's object. This is really interesting. And Dan wants us to explain the cosmic event horizon. We'll do all of that shortly on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And to help us along with all of those questions is Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Hi, Jonti.
Good afternoon. How are you going?
I'm well. Good to see you again. Nice T-shirt, by the way. Is that a comet?
That's...
Oh, and a dinosaur, yep.
the dinosaur fighting off the oncoming comet. These T-shirts are great, actually. I use these for when I'm doing outreach talks, and they're particularly good with kids. And I didn't realize when I got them, I just thought, these are fabulous. So these kind of printed T-shirts with dinosaurs and rocks from space falling down, and they're kind of funny and they're kind of cute. Didn't realize when I got them, I was giving all these talks, and someone came up to me and said, "Oh, is that from Happy Little Dinosaurs?" I'm like, "What's Happy Little Dinosaurs?"
Oh.
Turns out that there is a card game. That's one of the many, many kind of board game, card games that are out there. Fabulous stuff. I've got loads of games on the shelves behind me. Board gaming is great. Game out there, which is basically about the end of the times for the dinosaurs, and they're not happy at all in actuality, but it's apparently really good fun and it's kid-friendly. And apparently all these T-shirts I've got are free advertising for this game.
Oh, there you go.
So, yeah, there you go. I'm a walking billboard and didn't even realize it.
Yes, indeed. That's not a fat joke either. All right, let's answer some questions now. I'm going to have to put an apology forward straight up. I've been to my optometrist this week. I do have a little bit of an eye issue, so everything's super blurry, and they're all text questions, as it turns out. But we'll do our best. Rusty from Donnybrook is first up. I'm wondering just how many coincidences there are between the sun and the moon. First, we have the almost exact apparent size coincidence, which has enabled us to learn an amazing amount about the sun during solar eclipses. Yes, Fred and I have talked about that many times. Second is the rotation rate, which is the same for the sun and the moon at about the solar latitude where most sunspots are seen. What will this coincidence enable as we begin to inhabit the moon permanently? Will we be able to avoid most solar radiation storms by moving to the night side when large groups of sunspots are visible? After all, we don't want to be dug in at the poles forever. Could we do this with spacecraft in large orbits around the moon? Does the coincidence mean that large deposits of helium-3 may be found at certain lunar longitudes? Are there any more sun-moon coincidences that you know of? Thanks for the show. Moving on up, guys. You'll be number one soon. Well, we'll see about that, but we're happy where we are. Rusty from Donnybrook. That was more than one question, basically, but all centered around these coincidences that exist between the sun and the moon.
Absolutely, and the coincidences are really astonishing, and it's just our very good fortune to live at exactly the right time in the Earth's history where things line up like this. Because when the moon formed, the Earth was spinning much, much quicker, and the moon formed much closer to us. And at that point, when the moon moved in front of the sun, it will block the sun out totally by a long, long way, and you'd have a fairly underwhelming eclipse of the sun, to be honest. And as time has gone on, the moon has moved further and further away from the Earth. The further it moves away, the slower the Earth spins, the longer the moon takes to orbit the Earth, and the slower it recedes. And we're now in this very privileged window where most of the time, the moon and the sun are so similar in size that if they line up perfectly, the sun will be blocked out by the disk of the moon, and we can see the sun's outer atmosphere, and we get the wonders of a total solar eclipse.
Yeah.
Now, it doesn't happen all the time, because when the moon is near apogee, when it's furthest from the Earth, it is small enough that you instead get the ring of fire type eclipse. You get an annular eclipse where you get an annulus or a ring of the sun's disk around the moon. And that is presaging what is to come in millions of years into the future. So as time goes on and the moon keeps edging away from us, and as the sun continues to get very, very, very slightly bigger as well, because these things also happen, what that means is that as time goes on, we will get fewer and fewer total eclipses and more annular eclipses. And eventually there will come a day in millions of years in the future where we no longer get total eclipses at all, and we will see the final ever total eclipse from the Earth, which will probably be sad, but it's so far away in the future that we don't really have to worry about it right now. So that's coincidence number one, and it's effectively that the moon is about, I think it's 1/400th of the distance to the sun and 1/400th of the size of the sun. So, similar triangles that we learned at school and thought we'd never use mean that they're about the same angle in the sky and they block each other out. So that's all great. The second one, which Rusty has pointed out, I'd actually never really given any thought to be honest, but it is true that the length of the lunar month, the length of the orbit of the moon around the Earth, is about the same as the period of rotation of the sun, with an asterisk. And the rotation period of the moon, when compared to the background stars, is the same as its orbital period around the Earth compared to the background stars, because it's tidally locked. It's trapped in this orbit, so it always keeps effectively one face towards the Earth, one face away from the Earth. And that's a natural result of the tidal interaction between the two objects, and it's tied to these effects that are causing the moon to gradually drift away. Now, the sun is a fluid object. It doesn't have the same rotation period at all locations. It rotates quicker at the equator and slower at the poles. And that's thought to be part of the reason we get the sunspot cycles. What happens with that is that the equator rotates around once every 24 Earth days. The poles rotate about once every 32, 34 Earth days. And locations between have different rotation periods. So there is a latitude on the sun's disk that rotates with a period of exactly one lunar month. And so what Rusty's talking about here is the idea that when sunspots are at that latitude, if you've got one dominant group of sunspots, then one side of the moon will be getting hammered when those sunspots are creating activity, and the other side of the moon will see the sun when the sunspots are on the other side and they won't see them. Mm-hmm. The reason that doesn't mean you get one particular side of the moon getting all the solar radiation and the other side being protected is the fact that sunspots form at different latitudes on the sun and so go around at slightly different speeds. Early in a solar cycle, they're at higher latitude. Later in a solar cycle, they're at lower latitude. So the rotation period changes a bit. Also, you get multiple groups of sunspots at a given time. And the activity from a given sunspot group can hit the Earth and influence the Earth when it's at different locations on the sun, depending exactly what the magnetic field between the two is and the solar wind are doing. So I've seen cases in the past where we've had a flare and there've been aurora, and you look at it and the sunspot that had the flare wasn't dead center of the sun's disk. Your intuitive thing is that when the sunspot is bang in the middle of the sun's disk, anything it ejects will come directly towards the Earth. But in actuality, we've had a lot of aurora when the sunspot is offset because things follow a curved path, all this kind of stuff. So in that sense, I don't think there is any particular longitude on the moon that would be favored over the others, because on longer time scales, everything would totally smooth out, totally average out. On a given sunspot group, on a given event, you'll obviously have one half of the moon exposed and the other half protected by looking the other way, effectively. I think in terms of people wandering around on the moon and our spacecraft on the moon, it would be very inefficient to have to move halfway around the moon to get into shelter.
Yeah.
I think it makes more sense to drill down and hide a few meters below the surface where the rocks shield you.
Yeah.
And so while I love the idea of us having the ability to duck around the corner, you'd actually have to move quite a long way, and that would be inefficient and time intensive and all the rest of it. When what you can do is just say, well, we're just going to nip indoors and watch movies for a couple of days, we'll be under the shielding of all the rock and the rubble above us. That makes more sense. And in terms of other coincidences, the one that I think of that isn't really a coincidence at all is if you look at the bulk composition of the solid material in the solar system, it's to first order the same as the bulk composition of the sun, minus the gases. And that's just because everything formed from the same stuff. What's interesting is that the moon is depleted in the heavier elements and enriched in the lighter elements, compared to that. And on the flip side, the Earth is actually a bit enriched in the heavier elements and depleted in the lighter elements. They formed at the same place in the solar system at the same time, so you'd expect them to form from the same stuff. And so the difference in their composition is actually telling us about the story of their formation. And the fact that the Earth formed as a single object and then was smashed and torn asunder and formed the Earth and the Moon was formed from the lighter stuff that had floated to the top, so primarily from the crust and the mantle. And therefore you get this different in composition, where the overall bulk composition would be the same as the bulk composition of those materials in the Sun, but the differences are what tell us the story. So it's not really a coincidence, but it is an interesting link between a lot of them because we all formed at the same place at the same time from the same stuff, but the formation then shaped us.
Fascinating. There you go, Rusty. Hopefully that covered all your bases. Thanks for the question.
0G, and I feel fine.
Space Nuts.
And our next question comes from Trevor in Port Macquarie. With Comet 3I Atlas heading through our solar system at a record speed of around 60 kilometres per second, it's got me thinking about how fast an object like a comet or indeed a spacecraft could reach. I'm assuming Comet 3I Atlas has acquired some of this speed with maybe a slingshot around another star or two in the past. And as it passes the sun, it will probably pick up additional speed. Is there any limit to how fast a comet like this could reach if it continues to receive gravitational assistance from stars in the future? I know with a spacecraft, we use gravitational assistance by going around, say, Venus and back to Earth to pick up speed. But what would happen if we did, say, 50 times before heading off into the direction we want to go? So 50 passes, he's saying. Could we reach speeds well in excess of what deep space probes currently travel at? Or is there a level of diminishing return to this approach? Looking forward to your answer. Trevor, love this question.
Yes, this is really, really good fun. So it's a bit of both, to be honest. The long and short of it is that if you could set up the perfect chain of slingshot assists with ever more massive objects moving at ever greater speeds around, there is no real limit up until the point you get very close to the speed of light, because you can't get faster than the speed of light. But the challenge inherent in that is that you're transferring a bit of the kinetic energy from one object to another. You're stealing momentum through a gravitational slingshot. So if you fly by Jupiter and Jupiter gives you a kick to speed you up, Jupiter actually slows down a little bit. Because Jupiter is much more massive than you are, the change in its speed is much smaller. Its momentum is speed times mass, effectively. But you're taking a bit of that kinetic energy, and because of that, there's no real limit to how much you can boost. But any given encounter will only give you so much. The closer you get to the mass, the more of a kick you can get if the orientation's right. The faster the mass is moving compared to you, the more of a kick you can get as well. So you can imagine setting up a situation where you have a few flybys and you gradually get more and more boosts. And that's how people have taken the cheapskate route to the outer solar system. You get these missions that have a flyby of the Earth and a flyby of Venus and a flyby of the Earth and a flyby of Venus and a flyby of the Earth and a flyby of Mars and so on. And they get gradual little incremental kicks to get out to Jupiter.
Yeah.
It's also how we saw the Voyager spacecraft get a kick from Jupiter to Saturn, then Voyager 2 got a kick from Saturn to Uranus, and Uranus kicked it onto Neptune. And you got to speed up every time. The problem becomes you'll eventually hit the escape velocity for the solar system, and Jupiter's really good at doing that. Once you're at the escape velocity, you're not coming back for a second pass by Jupiter. So what are you going to get your next slingshot by? Well, if everything's lined up just right, you can do like the Voyager spacecraft did and do the grand tour where you get one to the next to the next.
Yeah.
But that's got a bit of diminishing returns because they're only so massive, so you can only get so much out of a given kick. You could possibly, in theory, aim out of our solar system to fly past Alpha Centauri and get a kick from that if you oriented right. And try and aim your spacecraft to get a kick from Alpha Centauri to kick you onto, I don't know, Sirius and get a kick there and bounce around and gradually accumulate speed. But eventually you'd again reach the escape velocity of the galaxy, and eventually you'd be on a one-way trip out of our galaxy. So it would be very hard to set you up to get to a speed that is ludicrous speed, a speed that is approaching the speed of light. You'd probably need to come incredibly close to a black hole to do that. And you'd need to engineer things such that you didn't get destroyed by the radiation and everything from the accretion disk around it. And you had your angle right so that you gained enough momentum to get much quicker. So you could probably play games like that. It's certainly really useful in the solar system. It's very effective at getting things up to high speed without requiring huge amounts of fuel. You can supplement it by timing the burn of your rockets and using your limited propellant to get the maximum kick possible. And I've read about special science fiction-y style maneuvers where you whiz around and you do your burn at the very closest approach to an object to get the maximum change in velocity and the maximum energy change for that given packet of fuel. I think it's called the Oberth maneuver or something like that. And it's really interesting because it, at first thought, it defeats common sense. So you think if you're speeding up by 1 meter per second, doing it anywhere in the orbit would have the same effect. But in fact, speeding up by 1 meter per second when you're traveling really quickly creates a bigger change in your final speed once gravity and everything works out than doing it when you're moving really slowly. There's all sorts of odd things like that going on. So there are games you can play with it, and you could set up a theoretical path that could take you millions of years to complete where you chain past objects. You have a little bit of control in your spacecraft to refine your orbit, refine your path so that you aim perfectly to the next target and effectively get a slingshot from each. But the practical limits are that unless you could get very close to a black hole, you're going to be limited to some degree, and it becomes, like you say, diminishing returns. Not because the physics of it prevent you from getting any arbitrary speed you want, but because the faster you're moving, the less targets there are to hit and the longer you've got to wait to get there.
Do you think the day will come, though, where we develop technology that stops us needing gravity assist, maybe ion engines or scramjets or whatever the things they're developing at the moment?
We're always developing new things, and as I've said before, you know, the one prediction you can make is that all predictions are wrong. Science fiction is amazing at coming up with things that have no grounding in current physics, but that suggest possible routes to do things that break the current laws of physics. And to some degree, everybody writes them off as purely fiction because they can't work in our current understanding of physics. But I remember that a long time ago, a lot of people were arguing that it was utterly impossible and physically impossible to have heavier than air travel. And our understanding of physics and the cosmos is limited by the quality of observations that we have. And our theories are exceptionally good at explaining things to the level that our observations can currently be carried out, and a bit more, but it's entirely feasible that as we get better at making observations, we reach the limits of where our current models are accurate, and we need new and better physics, and new things will come out of that. We'll also get more efficient at using the tools we know do work, and things like the ion engines, which they have tested with spacecraft, are interesting. Our common conventional kind of chemical rockets apply a very large amount of thrust for a very short period of time and burn fuel very intensively. And so you get a high acceleration for a short time. Ion engines are almost exactly the opposite in that they give you a very small acceleration, but that can be applied continuously for very long periods of time. And so they're much more efficient. And you can imagine stuff like that being scaled up. But the science fiction that leads to people moving at significant fractions of the speed of light nearly universally uses technologies that are beyond what our physics currently allows. And it's where you get the blurring of hard sci-fi and soft sci-fi, of the degree to which you have things grounded in current science and things grounded in fantasy almost. In science that is so advanced that it's magic to us because we can't explain how it works or know that it will. And so trying to say whether we'll ever get to a stage where our technology allows us to do these things quickly, to get to Mars in a week, to get to Pluto in a month or a week. You can imagine it is possible if you do the maths, if you accelerate at 1g, the acceleration due to gravity, and you can maintain that acceleration for a while, you get to very high speeds very quickly. So if you accelerate at 10 meters per second, after 100 seconds, you're going at 1 kilometer a second. After 200 seconds, you're going at 2 kilometers a second. So you gain speed very, very, very quickly. But you've got to use fuel very efficiently to do that. And a staple of a lot of hard science fiction that's kind of near future sci-fi relies on the idea of some form of drive system that allows you to maintain that level of acceleration for periods of hours or weeks or months. And if you could do that, the travel time to get to places like Saturn becomes manageable on a holiday. You could do what Fred's doing, but instead of going to Scandinavia, you could go and visit Titan.
Yeah.
If you've got that level of technology, and you do it in a certain degree of comfort, because what you do is your spacecraft's accelerating at 1G, so you feel an acceleration of 1G, and it's like you're on Earth. You don't need artificial gravity. You just have that short period halfway through the flight where you're weightless while the spacecraft turns around and starts accelerating at 1G in the other direction to slow you down for approach. And that's a staple of a lot of the more realistic sci-fi, but it still requires technology that we don't yet have, and we may never develop. Or we might. And, I'd love it if we did, but we'll just have to see.
Time will tell. But, Flash Gordon was the first to put rockets, that could re-land themselves. And now we can do that. There's all sorts of weird and wonderful stuff in sci-fi that has become reality. Thanks so much for the question, Trevor. This is Space Nuts with Andrew Dunkley and Jonti Horner.
0G, and I feel fine.
Space Nuts.
Our next question comes from Austin. He said, I've just been watching a long YouTube presentation on Hoag's object, a lonesome galaxy with lots of features that don't seem to fit with present knowledge. Do objects like that require a complete rethink of the standard model, or are there ready explanations of its features? Now, Hoag's object is astonishing, to say the very least. It's a very unusual ring galaxy. I know you've been doing some research on this, so we can sort this one out for Austin.
I have. It's beautiful. The photos are amazing. I do encourage people to look at this. It is one of a number of galaxies that we've seen that have this kind of ring-like structure. And the typical explanation is that you've had some kind of violent encounter between two galaxies where one has punched through the other really quickly and set up a shockwave, and that shockwave has propagated outwards, and the shockwave causes gas and dust to pile up and drives a burst of star formation. And as we know, the bulk of the most luminous stars in a galaxy are the hottest, brightest, shortest lived ones.
Yes.
And so it's natural that you'd get a ring where the shockwave has recently passed, where you've had a lot of massive stars formed that have not yet died, and you'd have a few reddish stars dotted through there, which are the stars that are about to die, and that the middle of the galaxy would look fairly yellowish and dull because there's no young stars there because all the gas and dust have been swept out. And we do see a lot of these kind of galaxies, but I've never seen any of them that is as symmetrical and beautiful as Hoag's object. Hoag's object looks like if you got somebody to make a perfect fried egg, and then they got two of those weird little poached egg rings, and they put one around the yolk, and then they put a much wider one around near the outside of the white. Everything between those two rings was lifted out and thrown away, and then the rings were taken away, and you were left with the yolk in the middle, and then an empty gap, and then a ring of white around the outside, although in this case a ring of blue. It is beautifully symmetric. There's a little bit of a hint of rotation there. It almost looks like a turning sawtooth blade when you look at it.
It does.
Which is leftover of the original rotation of the galaxy itself. The level of symmetry and stuff is really unusual. Now, what it suggests is that, and it should be said, nobody is absolutely certain how this object formed, but there are ready explanations that people have put forward. One which seems to have been shot down is that this is an extreme example of what's described as a bar instability. So you get these barred spiral galaxies where you get a big, long, straight central bar and then beautiful curved spiral arms coming off the end of the bar. You can almost imagine the curved arms joining up and then the bar disappearing for some reason. You'd be left with something that almost looks like this. That seems to be very disfavored for this object because of the shape of the central blob. The central blob is fairly circular rather than elongated, and barred spirals tend to have an elongated central blob. So that seems to rule that out, although there is still debate. The explanation that would make most sense is that this was the result of a collision between two galaxies at high speed, where you've almost got one galaxy punching through very near to the center of Hoag's object at high speed, triggering this shockwave, and then running off and vanishing.
Yeah.
Now, given the scale of that ring, the suggestion would be that the collision happened about 3 billion years ago. Billion with a B, not million with an M. The problem with this is that nobody can see any object that would be the bullet. It seems that would have disappeared. However, 3 billion years is a lot of time for things to happen. So I think the suggestion that most people have is that the bullet has been lost in the 3 billion years. There's also the fact that this is so perfectly symmetrical, so perfectly face on, that you could possibly wonder whether the bullet is actually hidden behind that central blob. In other words, the bullet has moved perfectly along our line of sight and we don't see it because the galaxy's in the way.
Yeah.
That would make sense to me. And that sounds like it's vanishingly unlikely, but to have this thing be so symmetrical means it must be almost perfectly face on, which means that the impact that created the shockwave must have been quite close to our line of sight. And so I can see some logical consistency there. But this is, and I know I say this all the time, but this is a really good example of that interplay between theory and observation, where whenever we see something new, we struggle to explain it, we get a better understanding of how the universe works and what all the models should say and what they should tell us. And that improves our understanding of other objects, and then we find something else that pushes the boundaries of that knowledge. It is clear that we do not have a definitive answer for this yet, and that's true for many of these objects in space. I think the argument of it being formed through a collision is fairly compelling, even though, you know, there are a lot of reasons why a typical formation would be unlikely. I'm just looking here at the summary of this on Wikipedia, to be honest, and that's got links to a few papers that have discussed this. Now, I'm sure some of the listeners are probably recoiling in shock at me looking on Wikipedia.
No, we actually do go there quite a lot because there's some very valid stuff in there. You just got to work your way through the garbage.
I stress this a lot to my students that you've been brought up through high school that Wikipedia is unreliable because it's an alterable resource and people can change it. And I've known friends who are teachers who set their class some really obscure topic to research and then deliberately go in and edit the Wikipedia page to say something wrong and then change it back after their class have done the work to demonstrate.
You're kidding.
It's cruel, but entertaining. What I stress to my undergrad students is that for astronomy, Wikipedia is a good first look quite often. And that's because we have people around the world who are into astronomy have a lot of knowledge and tend to be very obsessive, and I mean that in a really positive light.
Yeah.
And have their favourite objects. And if something is wrong, they're not backward in coming forward at fixing it. Added to which, a lot of the astronomical sites are not controversial, and they're not the kind of places that youngsters who want to be a bit rebellious will go to put something funny in. They're not going to be your prime targets for malfeasance, let's say. And so what that combined means is that a lot of Wikipedia articles out there are a relatively good first stab for astronomy topics. Now, they're not often spot on. You know, I've found things that have not included my own research when they've been talking about a subject, and that makes me sad. And sometimes, therefore, give a different opinion to what I'd have. And so it's always a case of use it with caution, go to the primary resources, but Wikipedia is really good at pointing you to some of the primary resources to get a good feel for it. And so I actually find using Wikipedia is often for astronomy things fairly reliable and fairly accurate because when an error creeps in, it is fixed very, very quickly.
Yes, that's absolutely true. I actually have found it very helpful in the past when I was writing the book about my grandfather in World War I, researching the minute-by-minute processes of the particular battles that he was in. I found a lot of good data on Wikipedia. So, yeah, don't write it off unless you're doing it.
It wouldn't surprise me. The kind of community that would look into that kind of thing probably has a lot in common with astronomy in that they'd be very detail-oriented and very precise and very knowledgeable about their particular topic.
Yeah.
But again, I'd have thought that it's unlikely that someone who wanted to do something funny would go to the report of a particular World War battle and edit it.
Yeah.
They'd probably go to Taylor Swift's Wikipedia page. I suspect the editors for Taylor Swift's Wikipedia page haven't...
Working very hard. I'm sure they are. Yeah.
So, yeah, it does not surprise me. It is a fabulous resource.
Yes, indeed. I think most of the people who want to stir things up go to Facebook, Instagram, or TikTok. That's generally where it all ends up. Thank you, Austin. Great question, and I would encourage people to have a look at Hoag's object online because it is quite a spectacular galaxy, well worth a look. Our final question today, Jonti, comes from Dan in California. He said, a new term I heard the other day was the cosmic event horizon. Could you talk about this a bit? Thanks, Dan. Yes, we this is another one that's a bit of a mystery. I mean, it's a thing. It's well known. It's not something that someone's sort of suggested may exist. The question is, where is the limit of this object? It's not really an object. It's a status, I suppose.
Yes. It's an interesting one, and more generally, an event horizon is a line that marks the boundary between things we can observe and things we cannot observe, in the simplest possible terms. So the event horizon of a black hole, anything outside the event horizon we can see happening. Anything interior to the event horizon we can't see because light can't escape. So the event horizon in that sense marks the boundary between what is observable and what is not. And that has led people to this concept of the cosmic event horizon or a cosmological event horizon. And when you look into it, there's actually two different definitions, two different types. One is effectively the maximum distance at which a source can be and have emitted light in the past that we can see today. Mm-hmm. And that distance is smaller than the real extent of the universe. It's kind of set by the point of the cosmological microwave background in actuality, because before that, the universe was foggy and the light couldn't escape. Now, the universe is very roughly 14 billion years old. I know the numbers are more accurately than that, but we'll call it 14 billion years. So and certainly my naive expectation would be that the most distant thing we can see is 14 billion light years away. And that is true for a given version of true. What it actually is the case is that the things we see that are 14 billion light years away, we're seeing, and I've got to word this very carefully, we're seeing where they were 14 billion years ago, and the light has traveled from that point for 14 billion years to reach us today. So we see them 14 billion years ago at a distance of 14 billion light years. But they are heavily redshifted. They're moving away from us. So the objects that emitted that light 14 billion years ago at a distance of 14 billion light years would now be 47 billion light years away. And light they emit now would never reach us because of the expansion of the universe.
Yep.
So what that means is that one sense of the cosmic event horizon is that we can see objects that can be as distant from us today as 47 billion light years in any direction, but we see them as they were 14 billion years in the past when they were only 14 billion light years away from us. And they've moved away since. So that is the event horizon in terms of events that we can see today that happened in the past. The other version, which makes my head hurt slightly more, to be honest, is the concept in cosmology that there is an event horizon which is the most distant objects that if they emitted a photon of light today could ever be seen from the Earth in the future. Mm. Now, they're moving away as well. Now, this seems to be well defined, and there's maths around it, and people have discussed it, that because of the event horizon, because of the expansion of the universe, you can't have an object that's arbitrarily far away, emit a photon of light, and expect that it would ever reach us. Because the expansion of the universe is such that before that photon of light reaches us, we will be moving away from it at a speed faster than the speed of light, and so it can never catch us up. It's a bit like the hare and the tortoise, and at some point, the hare is going so quickly that if you throw ping pong balls after it, they won't catch it up because it's going quicker than the speed of a ping pong ball. Yeah, hugely mixed metaphor, but you can kind of see what I mean there. Now, this is fairly well defined as a concept. It's this idea that objects far away from us emit light towards us, but they're receding, and they're receding from us at an ever-increasing speed. And we're receding from them at an ever-increasing speed, because the expansion of the universe doesn't matter where you are, it's all expanding.
Yeah.
And so there must be a horizon at some point, at some distance from us, where an object at that distance today would emit a photon of light, and that light would never reach us because of the expansion. I cannot find a definitive number for that size anywhere. I've looked around. There's a lot of mathematical equations that people use to quantify it, but the reason that we don't have a definitive number for that is that there are many models that look at the expansion of the universe into the future that all have very slightly different expansion rates going into the future. And different expansion rates would move this event horizon to different distances. If the universe is expanding quicker, then that event horizon will get nearer to us because you'd have to be closer to us to overcome this barrier of the expansion. If the expansion is a bit slower in the future, the event horizon will be further away. If you go, again, big up to the Wikipedia page, if you go to the Wikipedia page on event horizon and go down to the article heading Cosmic Event Horizon, there is a figure on the right that shows the reachable universe as a function of time and distance in the context of the expanding universe. That has lots of different things on it, and it seems to suggest that if light were emitted from the Milky Way galaxy now, right now, if we shone a laser up into the sky, the most distant object from us that could ever reach is at 26 billion light years from the edge of the Big Bang. That's not the same as saying 25 billion light years from us. This is where it all gets really, really, really confusing. They've got these light curves and things like this. Light ray emitted at 13 gig years from now would reach further out. So that figure suggests that there is that event horizon is something like 13 or 14 billion light years from us right now. If we emitted that light now, something further away from that than that could never see us.
Yeah.
But it's all up in the air. I can't, like I say, find an exact answer. And I think the reason I can't find an exact calculated distance is that if you even vary the expansion rate of the universe by a very small amount, you change the location of that event horizon by a very large distance. So it's just hugely uncertain. So at the minute, it remains a kind of theoretical conceit, a philosophical concept, but one that is important in us actualizing in terms of, in us conceptualizing, I guess, the idea that no matter how far in the future or the past you go, there will never have been a time when the entire universe is visible from here. So it's a bit like walking around on the surface of the Earth. No matter where you are on the Earth, you cannot see the whole of our planet unless you look at photos. Because from your location, no matter how high above sea level you are, there is always some of the Earth that you cannot see. And
even when you're in space.
Absolutely.
There's always another side to it that's
and
out of vision.
So when we get, it makes people's head hurt hugely, the idea that the universe can be infinite and finite at the same time, that we only see a small fraction of the universe that's out there. But to me, it does make sense when you think about it in the context of the Earth. I look out of my window here and I can see the beautiful Bunny Mountains in the distance. They're about 60 kilometers away, something like that. That's a long way away. I can see a large part of the Earth's surface, but that's a trivially small amount of the Earth. I'm aware at this instant of a pool of Earth around me. And in all honesty, the rest of the Earth could have disappeared and I wouldn't know. Now, I mean, obviously, we're still on our connection, so that hasn't happened. But we can visualize in that sense that the whole of something can be bigger than the fraction that we see. The whole of the Earth is bigger than the fraction of the Earth that you can see from any one location. The universe is a bit like that. And this is another way of discussing that, where it's discussing the maximum extent that you could see in the past, the maximum extent that you could see in the future. Yeah. So hopefully that, Dan, makes a bit of sense and gives you some direction if you want to read more about it, I guess.
Yes. It's when you do research on it, you come up with all sorts of theories about the universe. Is it infinite? Is it finite? But, beyond our capability to see because of its expanding rate and, the position of objects emitting light that could not reach us because of this. That it just goes on and on and on. It is really interesting, and it does get your mind swimming. But the bottom line is that the objects beyond the cosmic event horizon, there's just not enough time for that light to ever reach Earth. That's the bottom line, isn't it? So hopefully that explains it for you, Dan. Thanks for the question. It's been great. That's a couple of real thought-provoking questions today. Much appreciated. And if you do have a question for us, please send it through via our website. We've got a new batch of audio questions, 2/3 of which come from one person, but that's okay. We'll get through those, but we do need more. If you've ever considered sending a question, just never got around to it, jump on our website, spacenutspodcast.com, spacenuts.io, and click on the AMA link at the top and send us text or audio questions that way. And we look forward to hearing from you. Don't forget to tell us who you are and where you are from. And thanks to all our patrons too. I don't thank you enough. These are the people who enjoy the program and pitch in with a couple of dollars here or there to keep us afloat. You are amazing people. We never asked for that, but we certainly appreciate your support. And if you'd like to become a patron, you can find out more on our website. Not mandatory, but certainly appreciated. Jonti, you're appreciated too. Thank you very much.
That's an absolute pleasure. Thank you for having me. And yeah, the more questions, the better.
Yes, they're good fun. It's a great segment. I'm glad it's developed into that. It used to just be something that we tacked onto the end of one episode, but we've made it its own show. It's become bigger than Ben-Hur, really. And I'm wearing a wristwatch in the scene as well. Some people will understand that. Thanks, Jonti. We'll catch you soon. Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Also, thanks to Hugh in the studio, who couldn't be with us. He's taken a holiday beyond the cosmic event horizon. So we can't see his light, but I'm sure it'll return. And he can tell us how he got there when he gets back in about 47 billion years. And from me, Andrew Dunkley, thanks for your company. Catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.